Hello, today we're going to talk about structure 3.2.3 and 3.2.4. It's all about homologous series for organic compounds. So what is a homologous series? A homologous series is when you have a set of compounds that differ by a structural unit. So let's look at, if I have CH3, CH2, CH3, that's propane. CH3, CH2, CH2, CH3, that's butane. And that one is pentane. So the difference is each time I'm adding an additional CH2 group, which is often the case. It's very frequently CH2 is the additional unit. So these make up a homologous series. So they just differ by the number of that unit. So you can form homologous series for alkanes, alkenes and alkynes even. We're going to assume we're just talking about having one double bond or one triple bond for the alkenes or alkynes. Alkanes are going to follow the pattern that I showed you on the last slide, where you're going to add a CH2 each time. But effectively, you're going to have a formula that is always CnH2n plus 2, where the number of hydrogens is twice as many as the carbons plus 2. So like propane was C3H8, butane is C4H10. And so you're adding CH2 each time, C5H12. So another CH2 got added to the chain. If we are considering the alkenes, where there's just one double bond, it's going to follow the general pattern CnH2n. So like propene is C3H6, and then butene, or well, either butene, it could be but1ene or but2ene, we C4H8. But notice the difference here. The difference is still that CH2. You're still adding a CH2 group because it's only one double bond in the series. And then the next one would be C5H10, again for just one double bond. You're adding an additional CH2 for that chain. This could be any of the pentenes, pent1ene, pent2ene, pent3ene. The alkynes are going to follow, again, a similar pattern where you're at CnH2n minus 2, which works when there's only one triple bond in there. So propyne is going to be C3H4. Butane, one butane or two butane is going to be C4H6. And for 5 would be C5H8. But notice again, the difference is CH2. So you're going to see that pop up a lot. Now you can also have homologous series for organic compounds with functional groups, like alcohols. You're going to see CnH2n plus 1, and then the OH for alcohols. And the same idea, you're going to be adding a CH2 each time to make that alcohol bigger and bigger. You can do the same thing for halogens, CnH2n plus 1, and then the halogen X, whether it's fluorine, chlorine, bromine, iodine. And then you're adding CH2 each time. It's going to look a little different when you have something like an aldehyde or a ketone or a carboxylic acid, where it's going to have a double bond O. So you'll have your C double bond O. You'll either have an H, you'll have another carbon, or you'll have an OH for an acid, or you could have an O and another carbon for an ester. But effectively, whatever your chain is on this other side, you can get longer and longer chains, and that would still be considered part of a homologous series. So you'll just have to pay attention. So if they have the same functional group, just different numbers of carbons in the main chain, they're still considered part of the same homologous series. So why are homologous series important? It helps us to determine trends in their physical properties. So the larger the chain size, the more of those CH2 groups you add on, you're going to see a couple things happen. You will see an increase in boiling point and an increase in melting point. You'll also see a decrease in volatility and a decrease in the solubility in water. So let's talk about why this is. The longer the chain, the more carbons in a row you're going to have, all right? And the more total electrons you're going to have. So because it has more total electrons, it's going to have more frequent London dispersion forces, or stronger London dispersion forces. If you have stronger London dispersion forces, it will take more energy to melt or boil. Volatility, remember, is how well the compound will evaporate. So the more volatile it is, the more it evaporates. So if it has really strong intermolecular forces, strong London dispersion forces, then it will be less likely to evaporate. And then when we're talking about solubility in water, the best solubility in water comes when they have a small molecule or a very polar molecule, even better if it has hydrogen bonding. But effectively, the longer the chain, that's more of a non-polar group on the end of the chain there, and that makes it less soluble in water, which is going to dissolve more polar things. So because it is less polar, it will dissolve less in water. So at the end of the last slide, I just talked about solubility in water. I want to also relate that to the type of functional group. So I could have, alkanes, alkynes, so let's say hydrocarbons. Halogenoalkanes will be next. Aldehydes, ketones, alcohols, and then carboxylic acids. Okay, so this end of our list is more nonpolar, and therefore will have really only London dispersion forces, and will therefore be the most volatile and the least soluble in water. On our other end of the chain, of the carboxylic acids, you're going to be more polar. You'll see some hydrogen bonding in the carboxylic acids. You'll have the least volatility and the most soluble in water. Now, let's look at the intermolecular forces a little closer. Alcohols and acids will both have those hydrogen bonds. Halogenoalkanes, aldehydes, and ketones will be polar molecules and have dipole-dipole interactions. They won't have hydrogen bonds because you don't have that hydrogen attached to fluorine, nitrogen, or oxygen, but you will have dipole-dipole interactions, which are stronger interactions leading to less volatility and greater solubility in water. So now we need to rank the compounds in order of increasing volatility and provide an explanation for your answer. So I have bromopropane, which is a halogenoalkane, propanoic acid, which is a carboxylic acid, and propane, which is an alkane. So increasing volatility, we want to start with the least volatile. So it has the strongest intermolecular forces first. So we will start with propanoic acid, because it has hydrogen bonds, it's going to have the strongest intermolecular forces and evaporate the least. Then we will have bromopropane. Because it is somewhat polar, it's going to have those dipole-dipole interactions. And that makes it a little bit more volatile than propanoic acid that has the hydrogen bonds, but less volatile than an alkane. And so the alkane comes last, which is the most volatile of the group with only London dispersion forces. So this example predict how the aqueous solubility, so solubility in water, of the alcohols changes with increasing chain length and provide a reason for your answer. So as you have a larger chain length, it's going to decrease in solubility in water, because at longer chain lengths, you're going to have more of a non-polar end to your molecule. You'll still have OH, which can still form hydrogen bonds, but the larger the non-polar piece of that molecule is, the less able it will be to completely dissolve in water. It'll almost kind of repel the water, kind of like when you have oil in water, it'll form two layers because the non-polar, the London dispersion forces, are not strong enough to be able to break up the hydrogen bonding between the water molecules itself. So the smallest alcohols are most soluble, the big alcohols are less soluble. Okay, so this links well with the to nature of science and to our second tool there with 3D models. How can that help us visualize the invisible? Particularly when we're talking about chain length, it's going to help us see the physical differences between the members of a homologous series. It's also going to help us to be able to see how well something is going to be able to stick together. So for its volatility or its solubility, you'll be able to notice how it might be able to interact with water to form different intermolecular forces with water, or maybe it won't be able to interact well with water if you've got those really long non-polar chains. So 3D models are very, very useful for us to see the three-dimensional structure and get an idea of how that's going to interact in terms of intermolecular forces. Okay, and then this also links to structure 2.2, the influence of the carbon chain length, branching, and the nature of the functional groups on intermolecular forces. So again, the longer the chain length, the greater the size of the electron cloud. It just has more electrons, so it becomes more polarizable. And when it's more polarizable, it can make stronger London dispersion forces. So that increases things like boiling point and melting point and decreases volatility. We didn't talk about branching a lot in this section, but effectively, if you have very long chains, it's very easy for them to stack and stick together. But if you have branches, they are less able to stack together. So the straight chain ones are going to have more intermolecular forces and take more energy to break apart, whereas the branch ones are going to have less of those intermolecular forces, lower melting points, lower boiling points, more volatility.